Hello everybody. So this video, we are picking up with your second line of defense. We are still talking about your innate defense system, but remember the second line of defense, instead of using barriers to prevent things from getting in, we're talking about what happens when simple things do get in and you have non-specific responses, just a general response to make it go away. Right? That would be your second line of defense against antimicrobial proteins, all that kind of good stuff. So we have to talk about some of the microorganisms in deeper tissues, right? We have already discussed what phagocytes do. They act like Pac-Man, and they eat bacteria, just like Pac-Man does when you're playing that video game and he has to eat the little dots going around the maze map. Same deal. Your neutrophils are going to act like phagocytic cells and chase bacteria and consume them. This is what they do. Another big player in this innate response system would be natural killer cells. Your natural killer cells are cousins to your T cells, so they have that family lineage of wanting to seek and destroy, but instead of being elite SEAL team members, these guys go for the nonspecifics. So we've talked about how neutrophils and macrophages were like police officers in your SWAT team. Your natural killer cells are going to act more like Border Patrol or ICE. They're going to keep things on a next level higher than the police officers do, but still at home, if that makes sense. All of these things are going to help cause your inflammatory response system, which we are going to talk about more in depth in this video. We're going to talk about some of the proteins involved in this that are antimicrobial, like interferons and complement proteins. And the last thing we are going to talk about that is a non-specific response to an infection in your body is, of course, having a fever. Right? So some of the things that we have to talk about, we need to talk about some specific cells, right? I went the wrong way in the PowerPoint, I apologize. So we need to talk about some specific things in the cells. We know that macrophages are the next level SWAT team member that is evolved up from a monocyte. So monocytes are going to grow up big and strong into a macrophage if they grow up. And macrophages are going to be like your SWAT team members. They're not regular cops. They still are phagocytic cells, so they undergo that process called phagocytosis, where they will engulf an invading bacteria. But they are chief phagocytic cells. They're like the SWAT team members. Your macrophages are better trained to deal with things, whereas your neutrophils are generally like a Pac-Man, and they're just floating around eating invaders. You have a couple of different types of macrophages, and this is well worth noting. You have free-floating macrophages or free macrophages in your body, and they wander through like tissue spaces. So for an example, within your lungs, you have those air bubbles called alveoli. You have alveolar macrophages that kind of just float around the tissue spaces within your lungs, looking for bad things that you might have inhaled that they can consume and eat and get rid of. And then you have fixed macrophages that are permanent residents in a specific organ, meaning they never leave that organ and they will forever be there. One of the ones that we haven't talked about yet, because we've not talked about your digestive system, are called Kupffer cells. They are specific macrophages that live in your liver, that help filter the things that you have digested and absorbed from eating. Another one that you may have actually spoken about in ANP1 are the specialized macrophages that are going to live around your brain to help protect your nervous system from infection. They are called microglia. You may have spoken about those ones in ANP1, right? Neutrophils were just your regular cops, right? They become phagocytic when they encounter infectious material. So when they see a bad guy, when they see a bacteria that's inside you, they will get angry and attack it. They will they will be phagocytic cells and eat it. But otherwise, they're just kind of doing their thing within the community, trying to help clean it up. Right? That is the job of a neutrophil. They act more like the cops in all of these situations. So, what's going to happen when one of these cells undergoes phagocytosis to eat something, right? It's going to be facilitated by a process called opsinization. Pathogens and bacteria, so they can travel around, have a special coating of mucus, and they also have their own name tags. We have discussed when we talked about blood typing, a special type of protein on the outside of cells called an antigen that basically act as name tags for cells, right? For example, the cells in my lungs have little antigens on them that chemically mean, hello, I am a lung cell of Miss Bender. I belong here. Bacteria have their own antigens. And that is how we can tell that bacteria does not belong inside us, because it is not a name tag that came from our body, right? So opsonization means that we have coated a pathogen or a foreign invader with complement proteins. So this is like flag football. We have coated them with flags, or antibodies, which are the warning signs that we stick onto bad guys, saying, hey, this is a bad guy, we need to get rid of them. That is what an antibody is. Right? Antibodies are the most common type of complement protein that we are going to talk about here. So these cells typically identify pathogens because of the complement proteins that are stuck on the outside of them. You can get out. So after these cells have eaten your pathogens, right? After these cells have eaten the pathogens, they're going to destroy the pathogens, right? There are parts of the inside of cells, if you don't remember from basic biology, that act as stomachs and other organs, like the lysosome, that have or can become acidic. So there is some acidification and digestion within the lysosomes of cells that make enzymes. It will break down bacteria. There are, like, these cells, your neutrophils, natural killer cells, macrophages can also release cell-killing free radicals. And they will also activate other chemical signals and enzymes within your body. Right? There are other oxidizing chemicals within them as well, such as H2O2, which, if you don't remember what that is, H2O2 was your chemical formula for hydrogen peroxide. So parts of your body and parts of your cells will actually create hydrogen peroxide to help break down pathogens. This is also one of the things that your liver helps to filter out. Your livers are very good at turning hydrogen peroxide back into water with excess hydrogen bubbles. You can actually see that if you ever take a piece of liver that's uncooked. Like, just go to the grocery store. Any liver works. Cow liver, chicken liver is cheap, that kind of thing. If you take it home and you put hydrogen peroxide on top of that liver, it will boil. Well, it will look like it's boiling. It will become bubbly, and trust me, this does not smell good. If your high school biology teachers didn't do this for an experiment, be thankful that you haven't had to smell this before. But just trust me, if you add hydrogen peroxide to liver, the liver cells and enzymes are still active even after the thing is dead, and it will start causing the breakdown of hydrogen peroxide into hydrogen and water again, and it will bubble. Your liver is very good about this, but your body creates this hydrogen peroxide as an oxidizing chemical to help break down pathogens inside some of these cells. Right? So, talking about your natural killer cells here, right? It has that lovely army hat on, born to kill. Here you go for your lovely little image here. Natural killer cells are large granular lymphocytes. Like I said, they are cousins to your T cells. But they are walking around and patrolling around, double-checking your body and your cells' paperwork to double-check that you are indeed supposed to be here, just like an ICE agent, right? So what they are doing is they are free-floating around in your body, double-checking your cells to ensure that your cells have your antigen on it. So the cells that they are targeting as bad guys are cells that lack a cell surface receptor antigen, right? In any cell that they find that does not have a self-identifying antigen that proves it belongs to you, up to and including cancer cells and virus-infected cells, they will make those cells, or they will induce apoptosis. So what natural killer cells chemically do is they roam around your body and they will find a target cell that no longer has your self-identification antigen on it. And they will induce apoptosis, meaning they will inject the target cells that they have found without the antigens with certain chemicals that will intentionally cause those cells to commit suicide and burst. That is what the process of apoptosis is. It is programmed cell death, meaning the cell programs itself to die and burst. So These guys are pretty hardcore. Essentially, what we're talking about here is these natural killer cells are roaming freely around your body, and when they find cells that don't have their name tags on them anymore to prove that they are part of you, and that could be a virus-infected cell, because if you remember from basic biology, viruses hijack your cell, but in order for a virus to reproduce, it has to inject itself or its DNA into your cell, and it hijacks your cell's ability to duplicate and create its own proteins and DNA. So it does nothing but start replicating the virus's DNA so that it starts popping out more viruses. In that process, that cell will lose its antigens and self-identifying markers. Your natural killer cells can then pick up on cells that are infected, right? And they will make those cells commit suicide. Your natural killer cells don't care. Like, they are cruel. They go for it. Cancer cells are the same. Sometimes cancer cells lose that antigen. And remember, cancer is difficult to diagnose and find because cancer is your own body gone wrong. So sometimes cancer cells still have that self-identifying antigen on it, meaning these natural killer cells will ignore those cancer cells. Other times, the cancer cells have lost that antigen. They've lost their name tag. And if that's the case, the natural killer cell targets those cells and kills them. They secrete potent chemicals that are going to enhance the inflammatory response system then around the cells that they just killed. Right? So your natural killer cells are like nonspecific assassins looking for anybody that doesn't belong. And if they find cells that do not belong, they're going to go in, take them out, and then move on. They're double-checking everybody's passports. There has been some nifty and awesome research recently into natural killer cells for using them to attack cancer and that kind of information. So scientists are currently playing with trying to teach natural killer cells to attack specific types of cancer and specific types of tumors. It's what they do, right? So there's some nifty research around these guys going on right now. Hopefully we will find very good ways of controlling that so we will have better cancer treatments other than chemotherapy soon. And I really do hope that research takes off because no one deserves to have cancer. Right? So there are a lot of toll-like receptors. Toll, you guys know what a toll is when you're driving down the road. They're checkpoints where you have to pay to keep driving on the road. There are receptors on the outside of cells called toll-like receptors. That's what TLR stands for. And these are a number of what these receptors are. Some of them are found on viruses, others found on fungus. I'm not going to make you memorize this. I'm just letting you know that different receptors are on different types of sources, be it bacteria, fungal infections, like a yeast infection is a fungal infection, viruses, gram-negative bacteria, all this kind of stuff. Like flagellated or tailed bacteria. Different pathogens and different invaders to your body have different receptors on them. Your natural killer cells can read these and know what they're looking for. Right? So we're going to talk about inflammation now because we have mentioned it. So you have two different types of inflammation for your body. There's acute, which is short-term response to immediate bodily harm. And then you have chronic, which is ongoing due to foreign bodies or persistent pathogens, autoimmune disease, persistent injuries, that kind of thing. Your inflammation can become harmful and detrimental if it becomes chronic and it interferes with normal bodily use and function of whatever is wrong with it. A good example of this would be in our lovely classmates here that are into sports. There may be some time when you are playing your sport super hard and you pull a muscle, right? Like if you run and land wrong on your ankle, you may strain your ligament or your ankle, like ligaments or muscles. Your inflammatory response is going to kick up. You know that you didn't break a bone. It wasn't anything that bad, but you still partially or started to tear a muscle, right? So your ankle is inflamed. That can hurt and be uncomfortable. If you allow it to heal, that can be short term because that can just be your body's response to that tear. You let that tear heal. You exercise it a little bit so it heals as flexible as it could, but you take good care of it by staying off of your ankle for the next couple of days, and you just like treat it alternating hot and cold, like ice pack, warm pack, that kind of thing when you need to keep the swelling down and to make it more comfortable. You'll be fine and bounce back. But all of my long-term sports people know that if you keep trying to push through it and you just keep going and running on that partially torn ankle, you can turn that into a chronic issue where it stays swollen. And because it stays swollen, you're less flexible and you are more likely to further tear it or finish tearing it. That becomes an issue. Chronic inflammation can be very, very bad. Inflammation, because of that reason, can cause issues, but if you allow it to just be normal and short-term, it is one of your body's first line of defenses in the healing process and helps to protect your body. So it's a good idea to let it at least partially take its course, right? So, inflammation, let me find the right, there were more. There have to be more. Oh, okay. So inflammation happens, right? It's triggered whenever the body tissues are injured or infected. It's going to prevent the spread of damage and agents. It's going to also dispose of cell debris and pathogens, right? And it's going to set the stage for repair. That's its job. It's triggered whenever body tissue is injured or infected. Its job is to clean the space, prevent the spread of damage, and hopefully set up repair. So I'm going to use the example of the most heinous of injuries any man can suffer on this planet, a paper cut. Right? So when you get a paper cut, right, bam, you got that paper cut on your finger. It's the most painful thing on the planet. You are saying a few very blunt, choice curse words because of that. Flowing through your bloodstream and through your interstitial fluids and all that kind of good stuff, right? So flowing through all of that, you had a few natural killer cells. The natural killer cells notice a couple of pathogens because, gasp, there was a bacteria upon the paper that just cut through you. And your skin, that barrier that protects you from the outside world, has now been broken. So there is a cut in your skin, and blood, gasp, is exposed to the air outside. So that natural killer cell finds these foreign invaders and starts pegging them off one by one, just killing them. And as your natural killer cell kills some of these, it is going to send off a signal in a flare, right? Much like a flare gun. It's going to secrete some potent chemicals that are going to send signals to enhance your inflammatory response. Some of the first people on the scene from this are going to be basophils, and they release some histamine, and all of this act as flare guns for your neutrophils and monocytes to show up to the site of this dastardly paper cut. Right? What's going to happen then is the monocytes and your neutrophils, maybe macrophages if your paper cut is close enough to where a macrophage may live, They are going to start eating not only the bacterial cells that are now getting into your bloodstream because you're exposing your blood to air and somewhere on the paper, but they are also going to start doing phagocytosis and phagocytizing the broken skin cells from where the paper maliciously went through your finger and started breaking the cells to give you that paper cut. Your neutrophils and your monocytes are going to start to eat those broken cells to clean up the area. And the cleaner the area is, and the less jagged the lines are in that paper cut between the cells, the faster you can heal. Right? So what's going to happen is, as that histamine was sent forth as a red flag saying, we need help here, neighborhood watch, we have invaders, there is going to be a slight influx of interstitial fluid. Right? And the capillaries around the area are also going to dilate or become wider. This will help your white blood cells, your neutrophils, and your lymphocytes to get to the site of that paper cut faster. And it's going to flood the area a little bit with interstitial fluid and extra fluid. That serves a couple of purposes. We know this effect is going to happen because this is what's causing the swelling around an injury. Right? All that interstitial fluid ended up causing the swelling. The dilation of your capillaries and other interstitial fluid that is flowing in is also probably going to give the region a little bit of a reddish tone. So you're going to have some red swelling around the area of this paper cut. Right? However, that not only did that swelling or a sudden influx of liquid in the area make it a little bit red and swollen, and allow your other white blood cells to flood the area to get there faster. But that swelling and that additional interstitial fluid that's there has also hopefully prevented the bacteria that got into you from your paper cut from spreading to other locations through your bloodstream. It hasn't gone down your entire finger yet. That swelling is holding the bacteria near the cut. That way it can't go septic. Right? That's the purpose of that. At that point in time, all of these cells are going to clean up the bacteria, set the stage for healing and regrowth, and things will go on. Another side effect of this slight swelling and redness may be a little bit of heat. Your inflammatory response system also promises to warm up the area around that paper cut a little bit in the hopes that the bacteria that got in will be a little bit less comfortable and more likely to degrade when it comes inside you, basically. Not everything can live at the happy 90 plus degrees temperature that your body is, right? Bacteria, just like us, are comfortable at certain temperature levels. Like this slight heat from the area is in the hopes that it will kill weaker bacteria that cannot stand the heat inside you. However, because of this, you may feel some pain, right? Or you may feel some pressure in the area. This means that your cardinal signs of acute inflammation that we've been talking about are redness in the area, heat, swelling, and pain, or pressure in the region. Sometimes that also leads to impairment of function. When, like, for example, the ankle injury I was talking about earlier, you may have to stay off your ankle for a few days. So you may have impairment of function slightly. You guys should know your inflammatory response. You should know the signs of inflammatory response. Right? So just like above, we talked about your Toll-like receptors, right? Macrophages and your epithelial cells from your boundary tissues like skin all have Toll-like receptors on them. They recognize specific classes of infecting microbes, so this is a way for them to toll and recognize invading pathogens, right? When you activate, or when your macrophages activate any of these Toll-like receptors, it's going to release a type of protein called a cytokine. And these cytokines are like voices for your cells. They are proteins that are going to be sent out to tell surrounding cells, hey, this is here. This is a very short-term communication that's going short distances, but this is going to cause other local cells that may not already be infected to understand that there's an infection coming, and at that point in time, these cytokines may have sent the right help signal to cells that weren't infected, and the cell can be more protective of itself and put up its own defenses. Right? Right. Another type of proteins that may be released from this are called interferons. Interferons are complement proteins that are going to attack microorganisms directly, but an interferon is the polite way of saying this interferes with a virus's ability to reproduce. So, to put it in modern terms, an interferon interferes with your virus's ability to hook up with another cell, meaning it is kind of cock-blocking the virus. It interferes with the virus's goals, right? So an interferon is going to hinder a microorganism's ability to reproduce. Because if we remember correctly, viruses infect a cell and then make that cell start produce other viruses that will spread to other cells. Your cell's last-ditch effort to call for help and to save others but not itself is to send out some interferons to help with the fact that maybe these interferons will block the viruses, so viruses will not be able to use the neighboring cells as homes for its reproductive capabilities. Right? Chemokines are also communication proteins used. They're just used to communicate from longer distances rather than amongst neighbors. Right. So all of this stuff was set off to help your inflammatory response, right? Because part of inflammation, like I mentioned, is dilation of arterioles in the area, which is going to result in that interstitial fluid rushing to the area, or hyperemia, right? That's also going to mean that there is increased permeability of the local capillaries, along with this slight edema, in order to drain off the exudate or excess liquid that's being caused by all of this cell cleanup and the cell battle, as well as get better white blood cells in. But that exudate is also going to contain other proteins and clotting factors to help clot the injury, right? As well as antibodies, which will then swarm your foreign pathogens, right? So this exudate is going to move any foreign materials toward the lymphatic vessels, which will then be filtered in the lymph nodes. It's also going to deliver clotting proteins to make the bleeding stop and to repair the hole that is in you. Right? If we want to know how your white blood cells were, how do I put this, suddenly called forth to help, right? Your processes for this, leukocytosis is the release of neutrophils from bone marrow, if they were hanging out in bone marrow and being stored there. That means your neutrophils are going to hear the calls of help, be released, and then travel through your bloodstream to that paper cut. Marginization is what happens when the neutrophils sense through your chemical signals in your body that they are close to that paper cut, and they're going to start clinging to the walls of the capillaries around the inflammation and inflamed areas so they don't miss their stop, essentially. Diapedesis is the fancy term for when the neutrophils slip through the holes in the capillaries to go from in your bloodstream to into the swollen, inflamed area of your paper cut, right? And then chemotaxis is when inflammatory chemicals, like the ones we've all been talking about, are going to promote positive chemotaxis of neutrophils, which is going to make them hungry, and they're going to go into a feeding frenzy and start undergoing phagocytosis on everything they can see, right? Viral infected cells get a little bit more complicated than a paper cut because, as we've seen, a paper cut was just a paper cut. Bacteria got into you. Viruses target specific cells to infect, but you're still going to have an inflammatory response against viral infected cells. Interferons are going to enter neighboring cells, and then those neighboring cells are going to produce antiviral proteins that will block viral reproduction and prevent things from spreading, right? And they're going to all send chemical signals, like the chemotaxins that we've been talking about, like the cytokines, right? That are going to call for help, essentially, from your virus and viral infected cells. This is what happens when you have the flu. Normal flu infects the cells at the back of our throat. We know that we have the flu because our throats get a little bit scratchy. What happens is the virus will infect a cell in the back of our throat, and that cell will call for help, send out the interferons to try and mitigate the spread of the virus to other cells, and then a natural killer cell will come along because of the call for help and start killing the cells that are infected with the flu. As it's doing that, we are literally losing cells off the layers of the back of our throat. That is killing pieces of the back of our throat. We will re-heal from that, but in the meantime, because of this, it's going to start the inflammatory response system, and we're going to feel like we have the back of our throat is swollen, we're going to be uncomfortable, and things are going to feel scratchy for a few days, and it's not pleasant. This is what is causing the symptoms of the flu that we don't like the most, right? And the function for doing all of this is because that is antiviral. That prevents the virus from infecting all of the cells in the back of your throat so that you can continue, so that they have a job to do and they can keep doing their job instead of just being a little virus factory, right? This is also going to reduce overall inflammation that you feel. You're going to get some inflammation, but the fewer cells that are infected, the less inflammation you have to worry about. Right? So if you keep the spread down and things don't spread, the reaction can be smaller, right? This is also going to activate your natural killer cells, macrophages, neutrophils, anything else that needed to call for help will respond, right? Scientists are currently playing with genetically modifying some of these interferons, right? They are currently playing with these as antiviral agents for illnesses such as hepatitis, like viral infections like hepatitis, and genital warts, HPV, right? There are also, depending upon the type of MS an individual has, they are playing with a few interferon treatments for multiple sclerosis treatments. These are all being tested. Some of them may have reached the trial periods now. But this is all very fun and exciting if you get into pathology and virology and how to help and cure people, right? These are how new treatments are developed. They're currently developing genetically modified interferons. Please also bear in mind, we've been talking a lot about complement proteins, right? So we've been talking a lot about complement proteins. The most common complement protein we are going to talk about are antibodies, right? If we are thinking of complement proteins, there's about 20 blood proteins that circulate just around in your blood that are inactive. They're going to become active when they meet the thing that they fit into, like a puzzle piece. That's how chemistry works. On a very basic level, that's how chemistry works. But these are a major mechanism in destroying foreign substances. If you want to think about these complement proteins, they're made in the liver. They are going to supplement both the innate and adaptive immune systems. If you want to think about these complement proteins, think about them as the bullets, right? Your body is the gun that made the complement proteins, but the bullet is what's going to do the damage to the invading cells or invading pathogens, right? The complement proteins are our ammo. So what complement proteins are going to do is they are going to, if they find something they fit to and stick to, which is what they are designed to do, they are designed to stick to the outside of foreign pathogens. The more of those that coat the outside of foreign pathogens, the easier it is to recognize a bad guy. A good example of this, I can't think about one from the United States, but general practice and protocol in Japan, instead of the police potentially doing a high-speed chase on the highway with cars, we always view that as oh so exciting, and we see that in the movies and it's thrilling, right? But there is some harm involved in it, and there is the potential for the police officers or the bad individual that would cause a high-speed chase to crash into other individuals along the road or other cars. So other car accidents could be caused by that. The way they deal with that in Japan is not to have the police officers do a high-speed chase against the people that are getting away in a car. Individual officers in Japan are equipped with the equivalent, what we would call paintball guns in the United States. And they are trained, and their job is to not stop the getaway car, but peg the getaway car with as many of the paintball gun bullets as they have. That way, as the getaway car is traveling, it is marked in a bright neon paint, meaning it can be kept track of easily. Other police officers and other individuals can call in and say, hey, I've seen this car. So the cops know exactly where these individuals have traveled to. And then car dealerships and car shops that would otherwise have cleaned, like places where you take your car for, like to get a car wash and whatnot, can and will report the car as being at that location. Your complement proteins are like that. They are just floating through your bloodstream, and they are going to amplify any and all immune or inflammatory responses against a foreign pathogen once they get involved and start globbing on to foreign pathogens. So they're going to amplify your inflammatory response, and with some bacteria and some invaders, if enough of them glob on to the bacteria, it can kill the bacteria. It can cause certain cell types to burst, like pop like a bubble. If too many proteins are on it, it'll pop, right? But what you need to know about these complement proteins is they are going to enhance both your innate and adaptive, so specific and non-specific defense mechanisms in your body. So both the innate branch and the adaptive branches of your immunity respond to the complement proteins. And this is what opsinization is. It's when all of these complement proteins are going to coat the pathogen with themselves. Right? So we've talked about inflammation. We have not talked about adaptive responses yet. The last bag of tricks that your body has as a secondary defense mechanism is fever. Fever, or raising your body's temperature, is a systemic response. So your whole body is responding to this potential threat to respond to invading microorganisms. So that means that when you have a fever, your body has deemed the infection or threat to you as having gotten out of a localized area, so it thinks your entire body is at threat. So fevers are systemic or system-wide. That's your entire body. what fevers do is they make all of these macrophages and the leukocytes that we have been talking about. It's going to make any of them that have been exposed to foreign substances secrete something called a pyrogen. Pyro means fire. So as these neutrophils and macrophages secrete pyrogens, the more pyrogens you have, they're going to reset the body's thermostat, and they're going to make your body raise in temperature. So that means if your body is able to handle an infection and it stays minor, every time these neutrophils and macrophages have encountered this pathogen, you're not going to have that many pyrogens and you're not really going to feel an effect. But the worse the infection gets, the more pyrogens will be created as more and more neutrophils and macrophages encounter that pathogen and try to help clean your body. So eventually your body temperature is going to go up. There are some benefits to having a moderate fever, meaning because having a slight fever will cause your liver and spleen to save more iron and zinc. Remember, your liver and spleen broke down like red blood cells after your red blood cells were done or dead. This is going to make your red blood cells save more of that iron and zinc, right? Having a slight fever is also going to increase your metabolism, which is going to speed up how you heal and how fast you heal and repair from the injury, which is good. And also the fever itself, having increased the temperature from what bacteria normally lives at, can kill some pathogens, which is good. The downside to fevers is when high fevers can get dangerous, because if your body gets too carried away and you end up creating too many pyrogens and your fever gets too high, that heat can actually start breaking down your own body's enzymes and your own body's proteins, because heat denatures enzymes, if you remember from basic bio. So once you get to a temperature of like 104 degrees, go to the hospital. They need to give you medicine to bring the fever down. Sustaining a high fever at 104 to 105 degrees can lead to permanent damage to your body, because that's when your body starts breaking down its own proteins and enzymes. Like, please, please, please see a doctor at 104 degrees. With children especially, because they are small and tiny and still developing, it can cause seizures. High fevers can cause seizures if it starts affecting and breaking down your brain proteins and tissues. So please, go see a doctor if your fever reaches 104. That's the point at which you need medical attention and help. Like, go to a doctor at that point. But there you have it. That is the last of your innate immune system. We're going to start talking about your adaptive response system in your next video. If you have any questions, let me know.